Good evening to all. Now I am going to explain the UV spectroscopy part 4, relaxation of the selection rule. Relaxation of selection rules. Relaxation of selection rules. So here one is a spin selection rule. Spin selection rule. The metal complexes generally undergoes LS coupling. These metal complexes generally undergoes LS coupling. If LS couplings are considerably strong overlapping of the ground and excited electronic energy levels, where the different spin multiplicities takes place. As a result of this, the transition between electronic energy levels of different spin multiplicity are also taking place. This spin selection rule is relaxed and bands are observed in the spectrum. Bands are observed in the spectrum. Spin selection rule. Spin selection rule. So here metal complexes undergo generally metal complexes generally undergoes LS coupling. LS coupling. Metal complexes generally undergoes LS coupling. So here LS couplings are strong overlapping. Here LS couplings are strong overlapping of LS coupling is a strong overlapping of the ground and excited electronic energy levels. Ground and overlapping of ground and excited electronic energy levels. Electronic energy levels. Ground and excited electronic energy levels. So here with different spin multiplicity also takes place. Different spin multiplicity also takes place. So this different spin multiplicity transition between energy levels of different spin multiplicity is takes place. This is mainly spin selection rule is realized and bands are observed in the spectrum. So this is taking the different spin multiplicities takes place. Different spin multiplicity takes place. So different spin multiplicity takes place. So therefore these are the spin selection rule is relaxed and observed. Therefore spin selection rule is relaxed and observed in spectrum. So this is a relaxation of selection rule. One of the selection rule is a spin selection rule. Next, the second one is a Laporte selection rule. Laporte selection rule. So here mainly three conditions are there. There are three conditions for the Laporte selection rule. One is a departure from perfect cubic geometry or departure from perfect cubic symmetry. Second one is a DP mixing. Third one is a vibranic coupling. Laporte selection rule. Laporte selection rule. So Laporte selection rule is there are three conditions there. There are three conditions. So here how many conditions is there? Three conditions is there. Three conditions. One is the first condition is the is departure from perfect cubic symmetry. From perfect cubic symmetry. Cubic symmetry. Second one is a DP mixing, d orbitals and p orbital mixing. DP mixing. Third one is a vibronic coupling. Vibronic coupling. Vibronic coupling. Yes, Laporte selection rules. There are three conditions is there. One is a departure from perfect cubic geometry. Perfect cubic geometry means octahedral and yes, tetrahedral. These are the perfect cubic geometry. Other than octahedral, tetrahedral is a non-perfect cubic geometry. So nothing but here, here departure from the cubic geometry. So it is what happened? A defective geometry is obtained. Next, d orbital p orbital mixing is takes place. That also Laporte selection rule. Another one is a vibronic coupling. So departure from the perfect cubic geometry, cubic symmetry or geometry. So generally, in the case of the perfect octahedral system, perfect octahedral system, here G electronic energy level exists as they are yes centrosymmetric. So already we know octahedral is a centrosymmetric and tetrahedral is a non-centrosymmetric. So tetrahedral is a ungirated and octahedral is a girated set of the orbitals is there. So here see here, for example, in this case we have the take the octahedral. Octahedral is a says centrosymmetric molecule. Centrosymmetric molecule. Centrosymmetric molecule or geometry. A centrosymmetric molecule or geometry. So this is a metal here ligand. So this is a octahedral geometry. So these two are connection. These two are connection. These two are connection. Yes, opposite two ligands is connected. All ligands coincide at a single point. Therefore, center of inversion. So this is a G-rate orbital. G-rate. So octahedral is a G-rate. It consisting the T2G and EG set of the orbitals is there. So it is existing as a centrosymmetric molecule. Nothing but the center of symmetry is present. I. So all connecting points are coincide at a single point. Therefore, center of inversion is present in the octahedral geometry. If there is any further by which the center of inversion is removed, here center of inversion is removed temporarily or permanently, temporarily or permanently, then G-rate and G-rate energy levels existing. So once here center of inversion or centrosymmetry is here removed or permanently or temporarily, then G-rate and G-rate energy levels is existing. G-rate and G-rate energy levels is existing. Yes, yeah. So if there is any factor there is any factor by which there is any factor by which there is any factor by which the center of inversion is removed. The center of the center of inversion the center of inversion is removed. Center of inversion is removed. So remove S as a temporarily or temporarily or permanently, then G-rate and G-rate, then G-rate and G-rate, G-rate and G-rate. So energy levels is existing. G-rate and G-rate energy levels exist. So G-rate and G-rate energy levels is existing. So here center of inversion is a permanently or temporarily is a eliminated. Then G-rate and G-rate energy levels is existing in the octahedral geometry. Please take this one. Take a screenshot. So, in case of, for example, in case of Jahn-Teller distortion, octahedral complexes loses the center of inversion. So, in case of the Jahn-Teller distortions, octahedral complexes loses center of inversion. Thus, the Laporte-Barbadian transitions becomes Laporte-Hallowed transitions by relaxing orbital selection rule. For example, in case of Jahn-Teller distortions, Jahn-Teller distortions. In case of Jahn-Teller distortions, the octahedral complexes, the octahedral complexes, octahedral complexes loses, loses or lose the center of inversion, center of inversion, right? Loses center of inversion, center of inversion. So therefore, thus here a Laporte pervading transition, thus Laporte pervading transition, Laporte pervading transition becomes Laporte allowed transition, Laporte allowed transition. Laporte forbidden transition becomes Laporte allowed transition by relaxing spin orbital selection rule. By relaxing orbital selection rule. By relaxing orbital selection rule. So what happened in the case of the Chandler distortion in octahedral complexes? Here what happened loses the center of inversion. So therefore Laporte forbidden transitions becomes Laporte allowed transition by relaxing orbital selection rule. By relaxing orbital selection rule. Please take a screenshot. China. Hello? So Laporte forbidden selection rule converts to Laporte allowed selection rule. Now see the dp mixing, d orbital mixing with the t orbital. So in the case of the tetrahedral complexes, next one dp mixing. Next one, DP mixing. DP mixing. So here, in the case of the tetrahedral complexes, in the case of the tetrahedral complexes, E set molecular orbital related to pure metal orbitals. That is a dx square minus y square dz square. While T2 set of molecular orbitals are an admixture of d and p orbitals. Nothing but p and d orbitals. తెచ్చిందా అక్కడ రాకుండా రాజా yes so the d and p mix p orbital mixing nothing but admixture in the case of the T2 set. So due to this mixing the Laporte forbidden transitions become partially allowed transitions and to results bands in the spectrum. Okay, so that is a DP mixing. So DP mixing here, this is observed in the case of TD complexes. In the case of TD complexes, tetrahedral complexes. In the case of the tetrahedral complexes, the E set of the E set here mainly TD complexes here T E set and T2G set, two sets of the orbitals is there. So E set of orbitals, E set of molecular orbitals is related to pure metal orbitals. Is related to pure metal orbitals. Pure metal orbitals. Metal orbitals is related to pure metal orbitals. So those pure metal orbitals are nothing but the dx square minus y square dz square. So dx square minus y square and dz square. So while T2 set of orbitals, while T2 set of molecular orbitals is or are in admixture of dp means p and d orbitals. So this is the admixture of d and p dp. Which set is a T2 set? Each set is nothing but it is a molecular orbital is related to pure metal orbitals, and it is a T2 set or molecular orbitals are related to admixture of the dp, nothing but p and d orbitals. So the DP mixing due to mixing of Laporte, yes, what happened? Mixing of Laporte forbidden transitions become partially allowed transitions, results band in the spectrum. Yeah, due to this Laporte forbidden transitions, Laporte forbidden transitions becomes is partially allowed transitions. Partially allowed transitions. Here, partially allowed transitions. Partially allowed transitions. So this results in the band in the spectrum. Results band in the spectrum. Results band in the spectrum. Results band in the spectrum. Hey Babu, ఎన్నిసార్లు చెప్పాలి? Results band in the spectrum. Okay. So here what happened? Your T2 set is molecular orbitals are admixture of dp, p and d orbital. Due to this, Laporte forbidden transitions becomes partially allowed transitions. It results in the S band in the spectrum. So here mainly, for example, TD complex is taking, tetrahedral complex is taking. TD complex, tetrahedral complex is taken. So in this tetrahedral complex, mainly E set of orbitals and T2 set of orbitals is there. Yes, E set orbital and T2 set orbital is there. So this is a E set is a nothing but pure metal. Yes, this is a related to pure metal. T2 set is nothing but admixture. Admixture. So here these are the mainly dx square minus y square dz square. Here dz square. Here which is the admixture means p and d orbital. So therefore p here remaining d orbitals dxy, dyz, dzx, comma px, py, pz. So pz. So here mainly only G-rayed orbitals. Here G-rayed and un-G-rayed. G-rayed and un-G-rayed. Hello. Here G-rayed and un-G-rayed. Admixture nothing but p orbitals and T2 set of orbitals. So here G-rayed and un-G-rayed. Only pure metal orbital, only G-rayed. Please take a screenshot. So next one, vibranium coupling. Vibranium coupling. So vibranium coupling in the case of the transition metal complexes, so the metal ligand bonds do by break with results to each other as a result of this G-rayed and un-G-rayed vibranic energy levels exist in both in the ground as well as the excited state. So this is said to be vibranic coupling. As a result of this vibranic coupling, the transitions takes place between the G-rayed to G-rayed, G-rayed to un-G-rayed, un-G-rayed to un-G-rayed, un-G-rayed to G-rayed, resulting bands in the spectrum. This Laporte selection rule is relaxed partially and becomes allowed transition. So vibranic coupling here, transition metal complexes, transition metal complexes, transition metal complexes. In the case of transition metal complexes, metal ligand bonds, metal ligand bonds, metal ligand bonds do break, metal ligand bonds do break, results to break, results G-rayed and un-G-rayed vibranic energy levels, results G-rayed and un-G-rayed vibranic energy levels in ground and excited state. Ground and excited state. G-rayed and un-G-rayed vibranic energy levels in ground and excited state. This is said to be vibranic coupling. As a result of this, transition takes place. results. So here transitions takes place between 0 to 0, 0 to 1 0 to 1 0, and 0 to 0. So 0 to 0, 0 to 1 0, and 0 to 1 0, and 0 to 0. So this resulting in the bands. Results in bands in spectrum. In spectrum, resulting in the spectrum. So therefore, due to these transitions, here Laporte selection rules is a partially allowed. Due to these due to this transitions, due to these transitions, Laporte forbidden transitions, Laporte forbidden transitions becomes partially allowed transitions. Partially allowed transitions. Partially allowed transitions. Laporte forbidden transitions becomes partially allowed transitions. Laporte forbidden transitions becomes partially allowed transitions. Please take this one. This is called as a Laporte selection rule. This is called as a Laporte selection rule. Laporte selection rule. So next one, John Taylor distortion. Next, John Taylor distortion. So here, according to John Taylor theorem, any nonlinear molecular system, nonlinear molecular system with electronic degenerate state will be unstable and will undergo some distortions to result a system of low symmetry and lower energy, and thus the degeneracy is removed. As a result of this, system gets stabilized. The decrease of energy due to stabilization is said to be John Taylor stabilization energy. Yes. So John Taylor theorem. So John Taylor theorem. So according to John Taylor theorem, any non-linear molecular system, any non-linear molecular system, nonlinear molecular system, nonlinear molecular system, nonlinear molecular system with electronic degenerate state, with electronic with electronic degenerate with electronic degenerate state will be unstable will be unstable, and will undergo some distortion, will undergo distortion, So this results, here lower symmetry and low energy, lower symmetry and low energy, lower symmetry and low energy. This results lower symmetry and low energy. So once degeneracy is removed, as a result of this system gets stabilized by decreasing energy due to stabilization is said to be as Jahn-Teller stabilization energy. Yes, once degeneracy is removed, degeneracy is removed, degeneracy is removed. So what happens? The system gets stabilized. Yes, system gets stabilized. System gets stabilized. So this stabilized and mainly stabilized mainly due to decrease in energy. Decrease in energy. So this is called as a John Taylor stabilization, John Taylor stabilization energy, JTAC, John Taylor stabilization energy. So here symmetry and symmetry. Now see the symmetry and unsymmetry. So here, for example, T2G set is taken. T2G set. In this T2G set, T20, yes, T2G3, here T2G6 is a symmetry distribution of electrons. And here T2G1, T2G2, T2G4, T2G5 is a unsymmetric electron distribution. Unsymmetric. Yes. Now see the here EG set. EG set. EG set mainly here T2 EG0 no electrons or EG4 is a symmetry. Next to EG1, EG2, here EG2, EG4, EG2, 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 EG1, EG3 is a unsymmetric. Okay. So here EG2 is a special case. So EG2 is a special case. Here EG2. So one case is a S d x square minus y square having 1 dz square having 1. This is a symmetry. Hey Babu. So dx square minus y square 1, dz square 1 symmetry. Here another case is a dx square minus y square having 2, dz square having 0 unsymmetry, or dx square minus y square having 0, dz square having 2. This is an unsymmetry. So this is an unsymmetry. Here this is a special case. Please take this screenshot. So now stop to here. Next class tomorrow onwards.